So what we have to remember is that in every proportion, oh yeah, and by the way, see that right there? That's a fraction, right? That right there? That's a ratio. See this right here? That's a ratio. See that right there? That's a fraction. You get it? What's another name for a fraction? Ratio. So the ratio 7 to 5, or the fraction 7/5, that's the same thing. And then this whole thing, this whole bit, that's a proportion. So they're proportional, right? And in a proportion, and I'll just do a simple one. That true? Okay. In every proportion, if it's a true proportion, when you cross multiply, you guys remember you get the same number. So 1 times 10, 2 times 5, 3 times 20, that's 60. 4 times 15, that's 60. Okay? That's always going to happen. And we can use that to help us solve this proportion, because start with a variable, that always makes life better. I know that whatever x times 7 is, I don't know what it is, but I do know that it's the same as 5 times 10. Right? You guys all remember that? Who remembered that? Okay? So now I can just divide both sides by 7 and we got it. Okay? Let's look at that last proportion. So this is the same thing. We have a proportion. When we cross multiply, they have to be equal. The cross products have to be equal. We just have to remember something specific about multiplying here. You remember what it is? Hey, you focused up here? What's the one kind of weird thing you're going to have to remember here? There you go, distributive property. Parentheses, brackets, braces, absolute values, and fraction lines are all symbols of inclusion. So this fraction line, it's the same as having that x subtract 3 in parentheses. It is a symbol of inclusion. So it's not just saying x divided by 4 or 3 divided by 4, the whole thing. And it's also saying you got to do this up top before you can divide by 4. Or I guess we could divide each of them individually. So we've got to go 5 times x subtract 3 equals 4 times the quantity x plus 2. Now once you get it to there, I'm confident you guys can finish. So this is x subtract 23 subtract 3, so that's 20 over 4, which is 5, equals 23 plus 2, which is 25 divided by 5, which is 5. So by some miracle, Mr. Caller just made up some random problem and the answer turned out to be an integer. That was awesome. Okay, so why are we talking about ratios and proportions? Because we're going to talk about similar triangles. And we're going to use ratios and proportions to do cool stuff. Like figure out how tall a tree is. Or something like that. What's that?
Are we going to finish the Alice assignment?
Yeah, we will. But I wanted to do part of this lesson now because it's a long, kind of a longie. So we'll do part of it now and part of it later. So, okay, so we're going to talk about similar triangles. So, similar triangles. Similar triangles are going to have, well, what's going to be the same about them?
They have the same angles.
Same angles. So if they have the same angles, how does that affect the shape? Well, yeah, but how does it affect the shape? Like if this angle and this angle have the same measure, and and this angle here and this angle here have the same measure, and this one. So if all three of our angles, okay, all three of the corresponding angles have the same measure, how does that affect the shape of the two triangles? Do they have the same shape? Yeah, they have the same shape, right? Are they necessarily the same size? No. So whenever we talk about similar figures, I guess it's possible they could actually be the same size. You know, like they could be congruent. I guess congruent triangles would be similar because they have the same shape, but we never say that. I mean, when we're talking about similar, we're always talking about two things that have the same shape, but they have different sizes. And you guys are so good with similar figures. When I look at Carly from here, guess what? I can tell that's Carly. But you know what? If I walk up closer to her, yep, still Carly. But her head looks huge from here. What happens if I walk further away? Carly, go stand by that back wall. Let's take a look. Can we still tell it's her? In my vision, does she look the same size? Or does she look... She's only that big. Look, she's only that big. Right? And then if I walk up closer to her, okay, now her head's that big. Right? And then if I get up closer, her head's going to get like normal size, right? You can sit down. Good example. What if I take a picture of Logan? We don't want that. Let's take a picture of Chase. I want my camera to work later. So, sorry, Logan. I look at that picture. Chase's head is like that big. But, do we all still know it's him? How? It's similar, right? We get it. We see it. Even though it's a different size, it doesn't make any difference to us. And it's from our experience, you know, from the time you're a little baby. When your mom's clear across the room, you know, tiny little thing, and then she walks over to you. Oh, it's still your mom, right? You get it. Can you imagine how hard life would be if you didn't get that? That would be a little rough, wouldn't it? So similar figures, A, B, C, X, Y, Z. First thing we have to know about them is how to write a similarity statement. So we'll say something like triangle ABC is similar to triangle XYZ. So you can see, like our congruent, when we say they're congruent, we use that symbol, don't we? Okay? When we say they're similar, we say this. And there's a lot to this similarity statement, just like a congruent statement. Like I'm literally saying, angle A and angle X, what's their deal? Huh? Yeah? They're congruent. Angle B and angle Y? How come only one of you can talk? Here, you can't talk anymore. I know. Let's force. What about angle C and angle Z? What? Not kind of the same. They're actually... What? What was that, Rat? They're congruent. Okay. Now, what about side A compared to side X? Proportional. The crap does that mean? Oh, okay. So we've got side B here, and we've got side Y, and we have side C, and we have side Z. So I just use lowercase to make this a little bit easier. So the sides are in proportion. So whatever's going on with A and X, let's say A is twice as long as X. Then what do you know about C in comparison to Z? Yeah. And what do you know about B in comparison to Y? It's twice as long. Okay. So that's what we mean by proportional. So if we know some things, let's say we know this is 8, then if we're saying half, right, then 4. But that's not enough to figure out what C or B or Z or Y are. We'd have to know some more stuff. So let's say C over here is 10. Can you guys tell me something about Z? Yeah? It's got to be 5. It's got to be half the length. It's got to be 5. And then this one, it's 12. So what does that tell us about B? It's 24. So that's what we mean by proportional. You know, we have something called a scale factor. So the scale factor, we use a K. And I'm not really sure here if the scale factor is 2 or it's a half. Mason, what do you think? 2 or a half?
Half.
Okay. Cordell, what do you think? 2 or a half? A half? Ansley, what do you say? You're all saying a half? Kimball?
Probably a half.
Probably a half. So, yes, if you're saying you're going from here to here, so scale factor is directional, right? So if I want the scale factor from this triangle to this triangle, the scale factor is a half. If I want the scale factor from this one to this one, so this one's a half, this one's going to be, this one's going to be 2. So the scale factor, it depends on which direction you're going. And it will always say, find the scale factor from this one to this one. Okay? And sometimes it's hard to see what's going on, and there's a formula for it and everything. I'm not going to worry so much about the formula. We don't need to know all these sides in order to do the scale factor, but okay. So here, let's go this direction and find a scale factor. All you have to do is take two sides that correspond, okay, and then think about, okay, either the scale factor's 25 over 15 or it's 15 over 25. Right? It's got to be one of those two things. The ratio has got to be 25 to 15 or 15 to 25. Or I guess it could be 30 over 18 or 18 over 30 or 20. Okay, so the question is, which one is it, right? Well, there's a whole formula thing where you can talk about it, and it's like the pre-image over the image and all this stuff. But let's just think of it this way to make things, let's make life simple. Are we getting bigger when we go this direction or smaller? Smaller. Well, then your scale factor better be less than 1. Does that make sense? Right, Easton? We're getting smaller, so which one of these is less than 1? Well, this one is. So 15/25 or 3/5, that's the scale factor going this direction, from this triangle to this one. If we're going the other direction, okay, now I'm doing an enlargement, so this is a dilation still, right? Okay, so this is called a similar transformation, because it's not a congruent transformation like a reflection or a translation or a rotation. This is a dilation. And if we're going this way, if we're getting bigger, then make sure your scale factor is greater than 1. Okay? So if you think of that with the scale factor, that will make life much, much better. Well, I lost it. Oh, that's it. What if the scale factor equals 1? Yeah, So if two figures are congruent, then the scale factor between them is 1, because you're multiplying the corresponding side by 1 and getting a corresponding side, right? So if the scale factor is less than 1, okay, and still greater than 0, I don't think we want a scale factor less than 0, do we? Or what about 0? Would you want a scale factor of 0? Can anyone think of a reason we would want to scale something to 0? No, I can't either. Okay, so if our scale factor is between 0 and 1, then we're getting smaller. If the scale factor is greater than 1, then we're enlarging. And if you can just look at it that way, scale factor is going to be easy. All right, so that's the first half of this lesson. It's Monday. I know you guys are struggling. So we got an Alex assignment. Let's get that finished up.